In the early 2000s, Google engineers were drowning in raw data. They were processing massive datasets like crawled web documents and raw web request logs to compute derived metrics and inverted indices. The core problem wasn't the conceptual math, it was the execution. To process this data across hundreds of machines, engineers had to write bespoke, complex code just to manually distribute the tasks. Developers were forced to micromanage the mechanics. They had to manually open network connections, balance loads across CPUs, and write custom logic to handle inevitable machine failures. Software engineers were spending more time managing the physics of distributed hardware than writing the actual data processing logic. The MapReduce paper proposed a radical simplification. It created a strict boundary that hid the messy execution mechanics entirely inside a runtime library. The system requires the user to write just two functions. The first is map. It takes an input key-value pair and outputs a set of intermediate pairs. In a classic word count example, a single raw text document enters the map function, which then parses the text and spits out a vertical list of distinct words, each paired with the number 1. The user writes the second requirement, a reduce function designed to merge intermediate values sharing the same key. If the word the appears hundreds of times, those individual ones flow into the reduce function, merging into a single aggregated sum. When executed on a single machine, this functional primitive is conceptually straightforward. Restricting the developer to these two deterministic operations gives the MapReduce library the control it needs to handle the distribution of that logic across a cluster. When a developer hits execute on a 2000 machine cluster, the physical reality of the MapReduce runtime takes over. This diagram shows the overall execution flow. The user program forks into a specific topology. It establishes one central master, holding all state data, and numerous idle workers. Before work begins, the library scans massive input files and automatically slices them into distinct pieces. These splits carve the data into chunks, typically between 16 and 64 megabytes in size. Dividing a terabyte dataset into thousands of granular, independent splits is the absolute prerequisite for parallel execution and dynamic load balancing. Those granular splits immediately expose the primary bottleneck of commodity clusters. Network bisection bandwidth is scarce. If thousands of processors all try to pull data across the switches simultaneously, the network is easily overwhelmed. To solve this, Google relies on its distributed file system, which stores redundant blocks of input data directly on the local IDE disks of individual worker machines. Instead of assigning tasks randomly, the master reads location data. It purposefully assigns a map task to the exact worker node already holding that specific chunk of data on its hard drive. The worker machine then reads the input split straight from its local disk. Data locality reverses the traditional distributed model. MapReduce moves computation to the data rather than hauling massive datasets across a constrained network to idle processors. Once the data is processed, the map task generates intermediate key-value pairs, buffering them directly in memory. Map workers locally write intermediate data, saving network overhead. Reduce workers pull their partitioned data across the network, grouping and sorting it by key, using disk sorts if memory is exceeded. The reduce function then executes, appending results to the final output file. The system relies on atomic file renaming provided by the underlying file system to ensure that the final data is strictly consistent, even if multiple machines attempt the exact same task. This pipeline guarantees massive distributed sorts happen cleanly, funneling terabytes of scattered data into unified output files without users writing any routing code. When a single job requires 2,000 machines, hardware failure is not an edge case. It is a statistical guarantee. To survive this, the master sends a periodic ping to all active workers. If a machine goes silent, the master instantly marks it as failed. Any tasks currently in progress on that dead machine are immediately reset to idle and rescheduled. If a worker dies after completing a map task, that exact task must be entirely re-executed. Because its intermediate outputs were trapped on the dead machine's local disk, they are now completely inaccessible to the reduce workers. However, completed reduce tasks on a dead worker do not need to be rerun, because their final outputs are already safely written to the redundant global file system. Because the map and reduce functions are purely deterministic, the system doesn't need complex state synchronization to recover. It relies entirely on the brute force re-execution of dead tasks. There is a more insidious problem than hard failures: stragglers. These are machines that don't die, but run 100 times slower due to bad disk sectors or CPU bugs, holding up the entire job. A single, agonizingly slow machine can stall the final stages of computation indefinitely. To combat this, the master employs a backup tasks mechanism. As a job nears completion, the master defensively schedules duplicate executions of the few remaining in-progress tasks on idle machines. It creates a simple race condition. Whichever execution finishes first, the straggler or the fresh backup, triggers the official completion of the task. These execution layers yielded incredible results. In a benchmark test modeled after TerraSort, MapReduce sorted 1 terabyte of data on 1,800 machines in just 891 seconds. This chart shows the input rate during a sort test. Notice the sudden negative dip directly in the middle of the computation. That dip represents researchers intentionally killing 200 worker processes mid-computation. Because of the brute force recovery mechanisms, this massive hardware loss resulted in only a 5% penalty to the total execution time. By enforcing a rigid programming model, Google showed that a simple abstraction can mask the volatile, failing hardware of a